All right, so now we're going to discuss this concept of orthogonal polynomials. And so basically, if you will, it's like orthogonal polynomials, if you will, are the analog of orthogonal vectors. And one way to sort of think about this is that when you're dealing with functions, you're dealing with a infinite dimensional vector space. Okay, so the same way when you're working with vectors, it's like you have an inner product, like the dot product. You want to introduce a notion of an inner product on the space of functions. Okay, so you look at inner products, and so if you're given two functions, let's say f and g, then the inner product of f and g is oftentimes the integral from a to b of f of x, g of x, and then some weight function w of x dx. Okay, and this weight function is positive typically. All right, and then we say that f is orthogonal to g, right, if the inner product between f and g is equal to 0. And so the same way that you can take a basis for a vector space and then construct a orthonormal basis, you can do something similar with functions. Okay, so there's this idea of normal bases, right? And the construction is very similar to what you have with, again, with finite dimensional vector spaces. It's like, and you've probably seen this idea of the Gram-Schmidt process. Okay, so if you're given, say, a sequence of functions which are linearly independent, let's say x1, x2, and so on, and this is a sequence which is linearly independent. Okay, then what you can do is you can construct a new sequence which span the same space, which is orthogonal, right? I want to construct a new sequence. Let's call them U1 and so on, right? Which spans the same space. But which form an orthonormal basis for that space. Okay, so let's see how you go about doing this, and then we'll look at some special examples. So the idea, if you recall, is fairly straightforward, right? What you do is you keep projecting out components of the, so if you have already some subspace and you have a new vector, then what you do is you do the orthogonal projection and you subtract out this sort of orthogonal projection, and then you're left with a piece of the vector which is now orthogonal to the sort of the previous subspace spanned by the other entries. Okay, so this would be say xk, right? This would be the span of let's call that well, I think the index was subscript, okay, x1 to xk minus 1, right? And the orthogonal projection, it's like onto this span, right? And we've already sort of assumed that this span is equal to the span of u1 to uk minus 1. All right, so this orthogonal projection is given by the following. So the orthogonal projection of xk onto the span of u1 to uk minus 1, right, is given by the following. So you just take the inner product of xk with ui, right, and then you multiply it by ui, and you sum this over I equals 1 to k minus 1. Okay, so this is the projection, if you will, and then what is left over, right, is of course the difference of this. So now you can check that xk minus the sum of I equals 1 to k minus 1 of xk uk ui, sorry, xk ui ui, right, is orthogonal to the span of u1 to uk minus 1. Right, and that's a relatively easy thing to do. Right, you just take this xk minus sum I equals 1 to k minus 1 of xk ui ui, and you take the inner product with some uj. Okay, and you want j to go from 1 to k minus 1. Okay, so so if you write that, that's nothing more than xk comma uk, right, minus the sum from I equals 1 to k minus 1 xk ui, and then the inner product between ui and uj. Okay, so but we've assumed that the u1s to uk minus 1 are sort of orthogonal to each other. So this thing here is the Kronecker delta between I and j. So it's only 1 if I is equal to j. So when you take this sum, the only non-zero entry is going to be the term which involves xk inner producted with uj. Sorry, there's a j here. Okay, so you get xk inner producted with uj from the first entry, and then the only part which is left over from this sum is again the xk inner product with uj term, so minus xk inner product with uj. So that obviously is 0. Okay, so so that allows you to conclude that this object here, right, xk minus the orthogonal projection, is indeed orthogonal to u1 to uk minus 1. And then all that remains in order to compute uk is to normalize this entry. Okay, all right. So so you can write that down in the following way. So you can just have that uk is equal to the norm of xk minus the sum for I is less than k of xk ui ui. Okay, and you take the reciprocal of this. This is just to normalize the object, and then what you really want is this vector xk minus the sum from I less than k of xk ui ui. All right. So this is of course nothing more than what is called the Gram-Schmidt procedure. And of course, it's like now that we've expressed this in terms of inner products, you can imagine doing this now for polynomials instead of just vectors.